So much, Alistair. It's a true privilege and honor to be speaking here. Congratulations to Jesse. Congratulations, of course, to the centenary of the British Ecological Society. And as Alistair says, it's almost like coming home to be on campus here at the University of York. It's certainly not an outpost. At least during my 8 years, it was very much an inpost. In fact, the SEI board always talked about the York model as being the model for SEI globally, with its 7 research centers. I think that's still the case, and some former SEI colleagues here, so it's a great honor. What I'll be trying to do over the next 45-50 minutes is to, in a way, pose a scientific challenge to ourselves, where I'd like to lay out the evidence that we're moving into a very new juncture when it comes to human prosperity on planet Earth. And this is a social, ecological challenge, and it's a challenge that challenges first the notion that the planet is this static, predictable resource supporting the economy, that complexity and surprise is in fact the universal way the Earth seems to behave, and Peter talked quite a bit about that, we're referring back to some of that science as well. But secondly also, just as Thomas Friedman did this morning in the New York Times, make the case from evidence that we're moving from a connected to an hyper-connected, and from a hyper-connected to an interdependent globalized world. And it's no longer interdependent also only in the social, financial, economic spheres, but also in the ecological sphere. But this raises tremendous challenges in terms of the risks of surprise when the planet starts sending invoices back to the economy, which it has not done for better part of our history on planet Earth, but we're now starting to see evidence of that occurring. And the starting point is not surprisingly what I think is perhaps one of the most important messages from Earth system science, from the massive advancements in many of the scientists represented in this room, of the evidence from empirical observations that we've entered a new geological epoch, the Anthropocene, where humans now, 7 billion people multiplied by our industrial metabolism, constitute a quasi-geological force of change at the planetary scale. This is, as you know, something that Paul Crutzen, Nobel Prize laureate, launched in 2002. It's been more and more reviewed and published in science over the last couple of years, and I don't think it's come to a closure, but of course, the place deciding what epoch we're in and what is on our high school walls in terms of geological eras is, of course, decided by the Royal Society in the United Kingdom. And the Royal Society has, as you may be aware, a geological committee working right as we speak to take all the evidence and decide whether we are to scrap the whole notion of the Holocene. When I talk to my students, I say we now need to simply navigate and relate to a 369 world. We are in the mainstream of climate science, as has been stipulated this morning at least, moving towards a potential risk of a 3-degree warming, which is 3 times higher than the whole Holocene envelope. We're entering the 6th mass extinction of species on the planet, eroding ecosystem functions and services in support of the economy, and we are committed to 9 billion people on planet Earth. And this 369 world is a world that is shaped by humanity, for better or for worse. But the fact is, we're in the driving seat. And so far, we've been driving quite recklessly, but of course, if you're in the driving seat, there's an opportunity as well to transition towards a kind of win-win situation where we can avoid large risks and deliver prosperity for a world of 9 billion people. There is, as far as I know, no science to suggest that we cannot succeed in such a transition. But I also believe that science now needs to say, be brave enough to say that the growth without limits paradigm that has built well-being so far has been tremendously successful. But now we need to shift it around and rather talk about growth within limits. And just that small step, growth without limits to growth within limits, is a massive change in our entire relationship with planet Earth. The evidence is of course, overwhelming that we're moving in a very dangerous direction. It's been already put on the table here this morning. I think this work by Glenn Peters and colleagues is very telling because, as we all remember, these are, you recognize them, the IPCC fourth assessment scenarios, and we all remember when the A1 scenario were put on the table and so many criticized the IPCC, why put such, unrealistic doomsday business as usual scenarios on the table? Why assume that we're moving towards 11 billion people and that we won't do anything about fossil fuel emissions? Why put up a 4.2 to 5 degree average warming risk of this century? And of course we're following the A1 unrealistic path. we have the special issue of Science showing with a very, very strong empirical base that the Anthropocene is in fact founded on empirical observations. The hockey stick patterns of an era throughout the Holocene, in fact, with very little impacts aggregate at the planetary scale. And then 1955, 10 years after the Second World War, we're 3 billion people, and this is the point of the Great Acceleration, summarized not least in the, I think, seminal volume by the International Geobiosphere Program in 2004. And 2004 is important. It's not until 2004 that we put all the synthesis on the table that, in fact, essentially any parameter you pick from the Earth system that matters for human well-being shows the same pattern. A very little impact at the global scale up until mid-50s, and then the exponential growth. And you all know that, at this point here, Rachel Carson writes First Silent Spring. At this point here, the Limits to Growth report comes out of the Club of Rome. It's all shot down by conventional economists and policymakers. You could look at the curve and say, well, my goodness, perhaps you could excuse everyone because we didn't know where we're heading, but now we're up here. And there is a difference, therefore, in the juncture today, because we're standing, like Newton, truly on the shoulders of a giant knowledge base. The fact that we've emptied almost 70% of fish resources, the fact that deforestation, acidification, air pollution, climate change, as shown here, has the same pattern, is something that is the foundation for that new perspective. But it's not enough to recognize the pressures on the planet, because the pressures are not only about climate change as the only global driver. As Peter pointed out, and this whole theme for this conference, what is really critical is to understand that when we disturb the atmospheric system through emissions of greenhouse gases, the energy imbalance we cause, the big question is, of course, how resilient is the Earth system to buffer, to take that shock and still remain stable? The kind of ultimate resilience question. How stable is the Earth system to that pressure? And unfortunately, we know from great work of many in the room here that the Millennium Ecosystem Assessment truly put on the table that the last 50 years is a record in terms of undermining the resilience of our landscapes and seascapes to deal with that buffer. So that, in a way, is a kind of a double crisis, of a climate crisis, and when you would have wanted a strong planet, we've actually eroded it more than ever in terms of the period we've had in the Holocene. And then the space for development, I think one can argue scientifically, shrinks once you put the risk of surprise on the table. The 99-1 dilemma here is Stephen Carpenter, one of the leading resilient scientists on lake systems, who at one lecture said, there's strong evidence that 99% of change in our ecosystems occur at 1% of events. That in fact the big shifts from one stability domain from another, crossing a tipping point, is something that occurs often after long periods of incremental change, and then a sudden trigger and the system flips over. And that this reduces the space for humanity if we take a risk perspective. When talking to Swiss Re leadership just a couple of weeks back, they informed that they're earning more money than ever as the world's second largest reinsurance company, because they can raise their premiums very, very highly due to growing risks of different types of calamities. But one area where they're losing big way is in agriculture, because they're starting to see so many surprises in terms of droughts, floods, dry spells, pandemics, disease outbreaks. So they're losing money on agriculture because of the response in the biosphere. So how high is the risk of big impacts from the Earth system? I'll just go through a couple of them and then come back to the biosphere. And I'm not sure if this graph has been on already today, but I think it's a very important information for decision makers, not least in the world, that when you look at the albedo shifts over Greenland, and this is, as you know, NASA satellite data with days of the year on the x-axis, and in colored lines, the way Greenland, the way we would expect Greenland to behave, with almost 90% return of incoming solar heat back to space. But then in 2012, as you know, during a couple of weeks, the entire Greenland ice sheet is melting, changes color to a point where albedo is less than 50%. And the point of this is, you could argue that it may be the first, and it's an hypothesis, maybe the first example of a large biome, a large subsystems on Earth, shifting feedback direction from negative to positive. Because so far, to put it a bit simple, the Earth system has been our best friend. Mother Earth has largely dampened anthropogenic pressures. Peter pointed out the 50% absorption in the biosphere of our emissions of greenhouse of carbon dioxide, for example. But here we see a system that during 2 weeks actually goes to positive feedback. And as you may have seen, that Jason Boxer and colleagues at the Biodiversity Institute calculate that just that energy absorption increase during those 2 weeks exceed 300 exajoules of energy. Now, 300 exajoules is more than the entire annual energy used in the United States. So the paradox is that, at least momentarily, Denmark bypasses China and the US as the largest nation. Of course, it's just to show that under the hood of the Earth system, there are very powerful biophysical feedbacks, that when those kick in, you could argue that we are, so to say, more of the aperitif to a start of how things move on. As we are all aware in this room, of course, science, I think, and Alistair points that out, we need to start communicating better and synthesizing better. I think science is stepping up to the challenge increasingly. This is just one set of synthesis papers coming out from Earth system research. And I think the State of the Planet Declaration from the Planet and the Pressure Conference, which was the conference that I'm sure many of us were at, I think is the largest ever gathering of Earth system researchers or global sustainable development thinkers so far on this planet, 3,600 researchers, coming to the conclusion that our current development paradigm is too risky for humanity because it will cost too much on the long term. And I think it's a very important statement there to say that global sustainability now seems to be a prerequisite also to attain basic development goals. Basically to say we risk undermining the Millennium Development Goals if we do not also, in tandem, deal with global sustainability challenges. And this is a very dramatic shift because, of course, there's a very strong argument to be made that let's push development first and then deal with some of the costs. Now we seem to have come to what I think dramatically is put forward as potentially reach a saturation point. We are, in Will Steffen's words, starting to hit the ceiling of the hardwired intrinsic processes of the coupled, self-regulating, complex Earth system. And if that's correct, then of course it changes also the human dimensions and development paradigm, which I'll come back to. The last statement here, which comes out, I think, here is also as important. A great transformation is probably not only possible, but also very likely desirable for humanity. Science is also stepping up to this, as you may be aware, in the new Future Earth initiative. It is being launched as we speak on the train up from Manchester right now. I was together with Daniel Liverman, my co-chair of the Future Earth transition team, just putting our last edits in the acknowledgements of the report that we're now handing over to start and launch Future Earth. And Future Earth is, I think, fair to say, that the largest game in town when it comes to gathering force among the entire world's Earth system research community, both social sciences and physical sciences, to address not only a better diagnostics of the risks we're facing, but particularly looking at the human dimensions, economics, institutions, governance, behaviors, and solutions towards global sustainability. And this is led, as you may be aware, by not only scientists, but also funders of science, service providers of science, a number of UN agencies, and simply a very exciting initiative of merging the current global environmental change programs. Merging the current global environmental change programs. The only one of them being part, but not merging, is the World Climate Research Program, but the others will be merging. The Earth System Science Partnership, the Human Dimensions Program, Diversitas, and IGPP. Now, is the world outside starting to understand that we're in a globalized, interdependent era with complexity, uncertainty, and feedbacks? Well, I think, yes, increasingly. This is how The Economist normally portrays turbulence in the world. This is the Lehman Brothers vortex from 2008. But the world also welcomes the humanity to the Anthropocene roughly 1.5 years ago. And The Economist, which I pay a very high respect to, a wonderful British Business Weekly, has this beautiful, typical British understatement, which I think is a good reflection of how science feels today, which is that when reality is changing fast and furious suggests it should, a certain amount of nervousness is a reasonable and that this is probably exactly what we're talking about, that when the Arctic sea ice suddenly over a couple of months loses 30% of its cover, that is a scientific shock, as it were, and therefore also something that clearly points at the world changing faster than theory stipulates it should. And therefore nervousness and nervousness in my mind is a precautionary approach. World leaders are starting to understand this. I don't know if you've read the Ban Ki-moon Global Sustainability Panel report to Rio. If you haven't, it's worth just flipping through it, because it is the Brundtland Commission equivalent to the Rio Plus 20. It is, I think, the first time policymakers in the world recognize the risk of tipping points, recognizing that we need to relate to this globalized environmental challenges we're facing, and that overall leads to the conclusion that we have a window as scientists also to inform new policies towards a global sustainable development. So that's just on the intro. Now I'll dig a little bit into where are we in terms of evidence on regime shift. Peter has already covered parts of this, so I can flip this through quite quickly. So yes, we're starting to learn that ecosystems from local lakes to big biomes like the Amazon and Arctic regions and tundra systems and multiple stable states. We built our economy based on this assumption that you can push systems quite far and they will behave like a Walmart supermarket. You know, you just go in, you pick your resources on the shelf. If a resource goes down, you just expect the resource to go back up with the new policy. While in fact, we have not only thresholds, but also often hysteresis, which means that you push a system across the threshold, it moves into an undesired state, the cost to bring it back will be much larger than the gains you got by pushing it over the threshold. And that we have a lot of evidence from empirical observations that this is occurring. We call this resilience. We talk of three, let's say, characters of a resilient system. And I'll be focusing only on the first one, which is the persistency dimension, the robustness component of resilience, which is how much disturbance can a system take before tipping over. But of course, resilience is increasingly also addressed in terms of capacity to adapt. So you're in a desired state of attraction, and the system gets pushed back and forward of various types of stress. And what is the ability to adapt within that stability domain? And an emerging area of research that we're engaging much, much more in is that once you're beyond adaptation, once you're pushed over a threshold and the system collapses, be it a farming system in the Sahel or be it a financial system, what are the elements that such a system needs to be able to transform in a completely new direction? What is the ability to move out of a crisis into a new desired trajectory? Now, the evidence that of having to take persistency and coupling it to complex drivers in the biosphere is growing. I think that was postulated quite clearly before lunch. I think this work that came out quite recently, I mean just a month back, by Karnen and colleagues, is important in this context because it shows that our old assumption that the biosphere feedback when we move in and out of ice ages is somewhere in the order of 800 years may have been a wrong conclusion, and that in fact the biosphere feedback is closer to 0 to 200 years, meaning that, and I'm sure that was covered before I came, that in fact we can only take ourselves up to the warm interglacial levels of temperature through biosphere feedbacks. Our position to the sun and our position in the universe won't be enough. But the growing evidence that this feedback occurs faster is in my mind also a kind of a warning signal that we may see big biosphere feedbacks, as for example analyzed by Peter earlier, faster than we earlier thought we should. And this was discussed earlier, the fact that so far the sink in the biosphere is remarkable. And I think the Global Carbon Project and others, this is work by Valentine and colleagues, is absolutely remarkable in showing this. I think one of the most interesting conclusions here, though, is the fact that in 1960, the estimate is that the terrestrial and marine ecosystems absorb 2 units, 2 gigatons of carbon. And today, that level is estimated to 4.5, which means that the Earth system clearly in the Holocene stability domain is so to say behaving just as resilience theory stipulates it should. It is operating its biogeochemical processes, it's kind of using its entire palettes of biomes and systems to cope with our anthropogenic disturbance, and it's doing that so far quite well. The question is, though, how far can we push the system before that dampening capacity is reduced or potentially even reversed? Now, we've just launched or ended a work from the Arctic Council that came to us, the Arctic Council being the group of nations, the 8 Arctic nations, asking the question, what are the risks of big tipping points in the Arctic? And work by Tim Lenton and colleagues showing that, yes, there are risks of subsystems flipping in the Arctic, and I'll come back to particularly the risk of the Arctic vortex shifting. We talked just about Greenland, and you may have seen the work by Dorothy Jensen and colleagues at the Bohr Institute showing that potentially we need to rethink the resilience of the Greenland system. And I think that's another example of the surprise elements in science currently. So this is ice core research in the large NEAM project over the past 5 years. It is focusing on the Eemian integration, which is a good reference point for us because it's the last integration we had. As you're certainly aware, this is an era where we, during 4,000 years, with quite good robust science, indicate that we had at least 2 degrees higher temperatures than today, or 4 to 6 degrees higher in the Arctic region. And the conclusion has always been that during this period, Greenland must have melted. It must have essentially melted down. But this research shows very convincingly that that was not the case. That in fact, the level of sea ice in Greenland in the Eemian warm period was probably just 120 meters lower than today, and roughly 350 meters lower than the Eemian, which could only contribute to roughly 2 meters sea level rise at the global scale. So that's good news. That's in fact tremendously good news because it tells us that Greenland is probably more resilient than we previously thought. Now, the drama is that we know with quite high certainty that the sea level during that Eemian period was 6 to 8 meters higher than today. And of course, the drama then is, where is the residual? Where is the missing 6 meters? And the only answer can be Antarctica. So the paradox is that we may be moving into an era where we simply shift from having always assumed that Antarctica is rather resilient to being the more dark horse in the system, while Greenland may be a much more robust system. And this is just to postulate that we still have many scientific challenges in understanding how the Earth system operates, but also that we have so much evidence of the surprise element, that we get sudden feedbacks that require from us a new type of, let's say, relationship where we take these kind of risks much more seriously. You've probably seen this fabulous set of NASA data, which you actually can download now basically on a monthly basis, showing temperatures anomaly across the planet. I use this very much when I talk to Swedish politicians because in 2010, climate skeptics in Sweden stepped up, where the hell is global warming? We were freezing like hell up in Sweden. It was the coldest winter since the Second World War. And you put this graph up, you say, well, you can't use Sweden as a reference point for the world. Because it was a cold pocket, a very cold pocket in a world that still has a record high anomaly as compared to average temperatures pre-1960. And you've of course seen the growing set of peer-reviewed articles coming out to indicate that the cold weathers both in the UK, Nordic regions, Russia, and North America may in fact be linked to the collapse of the Arctic vortex in 2008 and the shifts in the jet stream pushing down cold Arctic air to our latitudes. Now that is a paradox, a grand paradox, but it's something that is consistent with the stochastic behavior of weather systems. Another example of surprise. We're at the Resilience Center hosting a whole database now on regime shifts to try and put on the table what is the empirical evidence that nature behaves in this way. And it is a long database today. So this is one of those, I think, stronger and stronger evidence bases in marine systems, from both saltwater marine system, freshwater system tipping points. We've done a lot of research on the Baltic, showing that probably the Baltic tipped over into its current anoxic 60% dead state in 1989 after a long period of unsustainable management, eutrophication, overfishing of cod, tipping over in 1989 because of 1-2 years of poor oxygenization, and today stuck in an undesired state with algal blooms being basically a systematic part of the system. Interestingly, there's a lot of progress in reducing eutrophication to the system. The last water treatment plant was built and inaugurated just 1 month back in St. Petersburg. St. Petersburg has not had any water treatment up until 1 month ago. And this is great success, but still the system is stuck. And there seems to be a strong hysteresis here. And the interesting thing is that this is not only eutrophication, it's also climate change and the loss of the top predator, cod. That means that sprat explodes. Sprat eats zooplankton. Zooplanktons are the grazers. The grazers disappear. Phytoplankton explodes, thrive even more because of nitrogen and phosphorus, and the whole system accelerates into a locked-in new state, which means that biodiversity, climate change, and eutrophication is interacting in the system. The work by Janestis and others showing that top predators do matter for tipping points in ecosystems. The work showing that once we empty roughly 30% of fish stocks in the world, seabird populations seem to abruptly lose in numbers. And then, which was talked much more eloquently by Peter earlier, the risk of a tipping point to a savanna state in the Amazon. This is work by Carlos Nobis. I think the only thing to add there is that the complexity here is not only about climate change, it's also about the growing turbulence in the system when you deforest and change land use. So the system can be more vulnerable due to multiple drivers of change. And of course, the very challenging and debated scientific article by Anton Barnowski and colleagues showing that we seem to be moving toward a trajectory where we may have a tipping point on global biodiversity in mid-century, which is, of course, a very dramatic statement, scientific statement indeed. What I'd also like to just highlight in this context is the risk of underestimating the interconnectivity of the Earth system. This is a picture I'm sure you've seen. It's palm oil plantations on Borneo. 75% of the Indonesian rainforest is today lost to palm oil. This is often portrayed as being a massive, rightly so, massive risk for indigenous communities. It's a collapse of biodiversity. But increasing research, for example, by Peter Schneider and colleagues at John Foley's Institute, showing that if we lose the large rainforest systems, of course you get a warming in these systems, but you also get feedbacks across all the way to inner China and to North Africa. So the interconnectivity of systems do matter. This is work we're doing together with Huub Savenay and colleagues at TU Delft, which, if it's correct, in fact, I think is potentially geopolitical dynamite, because this is showing that we probably underestimated the role of the biosphere in generating stable rainfall conditions in different parts of the world. We've always assumed a much larger role of the oceans in terms of evaporation and moving in big weather systems releasing rainfall. But in red here you have the regions in the world which indicate at least 80% of rainfall coming from adjacent land areas. So for example, China here is a region that depends to more than 80% of evaporation from forests in Ukraine all the way to Russia and the Baltic region. Similarly, for the wet savanna regions here, depending on rainfall evaporation from Southeast Africa, and the same thing for the southern parts of the Amazon rainforest. Now, if this is correct, then of course it requires a completely new relationship between nations, because the Russian management of forests is therefore the stability of the Chinese food supply. So all this lands, I think, in a conclusion, a kind of partial conclusion, that we need to be able to keep more than one ball in the air at the same time. And as you know, politically that's very difficult. Today it's only jobs, jobs, jobs and growth. Very little climate. Biodiversity, essentially nothing. The biosphere, when does the biosphere come up on the political agenda? And I'll just run through a couple of examples, putative examples, of where I think one can now start to see evidence that this is an absolute necessity. And we recently published a paper kind of to set the scientific agenda, led by Brian Walker and colleagues, to say that, well, now it's not only about the kind of biophysical systems on the planet. We're starting to see interactions with human health, the economy, and the kind of social dimensions in this interdependent planet. You may have seen this paper by Robert May and Simon Levin in Science, which came out on the ecology of bankers, showing that it seems to be that the financial system has the same kind of behavior that Peter pointed out of growing variability and then a slowdown prior to crisis. So basically, what can we learn from ecology for bankers? This paper was published 6 months before the financial crash in 2008. And Simon Levin gave a talk about this in Singapore, where I participated just a couple of months back, and he said, I'm sad, I didn't only write this paper, I sat and didn't read it. So he wrote it but didn't read it, which was a pity. But this is one example of the kind of lessons that can be learned between systems. This was covered also earlier, the growing science of being able to use indicators of variability as a proxy to warn prior to big tipping points. This is in fisheries. But the conclusion of this work by Unsi Biggs and colleagues from our center is that, in fact, it's so difficult, as Peter also pointed out, that perhaps we need to start defining critical indicator levels rather than be able to monitor variability in the systems, which is a way of arguing for some kind of global sustainability criteria. You may have seen some of this science, which I think is very dramatic, which points at evidence that even the Arab Spring, which of course was a very dramatic example of a young, well-educated, socially connected, new generation moving to the streets and not accepting decades of dictatorial oppression, but more and more evidence showing that right at that time, phosphorus prices rose by 150%. And Putin and Australia shut their export borders on cereals, which shot up food prices by over 100%. The reason why that export was shut down was 12 years of drought in Australia and forest fires in Russia. And that these two factors together, with oil price rises at the same time, may have triggered and gotten the Arab Spring to scale, particularly in Egypt. So food prices affecting also the going to scale of this kind of large social change, meaning that we're starting to see examples of social ecological interactions at the regional scale, hitting at the short term for the first time. So that's one kind of example. The other one, we had a large conference together with the health science journal Lancet just a couple of days back in Stockholm, showing that we now need to connect the whole global environmental change agenda with the health agenda, particularly when it comes to zoonosis, when it comes to infectious diseases transmitted from wild animals to domestic animals, normally, and domestic animals to people. And that in fact 60% of the emerging large infectious diseases originate from the biosphere directly. And you may have been reading about the H7N9 avian flu infection that is right now growing into scale in Shanghai, being one of those examples of nervousness, because so far 6 dead out of 24 sick is one issue. But the other issue is that apparently the avians do not die this time. So there's no way of finding the source of where this is happening. This is one example of triggers occurring in a world that is increasingly socially connected, but evidence also showing that the risks grow in terms of pace of the pandemic because of globalization and potentially also the change in agricultural patterns in the world. The cost of these shocks increase, and the evidence is very clear. The large outbreaks of infectious diseases coming out of zoonosis are tremendously much higher than in the past. We're talking kind of budgets which are in the order of 50, 60, 70 billion US dollars per year. And these are just a few examples of the kind of social environmental interaction we're starting to see play out at a larger scale. So then my last part is to ask the question, well, what does all this mean in terms of a paradigm for development? How can we translate this science of social environmental risks into some kind of way forward? And before doing that, I just want to ask or put this as a challenge to us, that what if in fact, I think many try to give the impression that environmental science has been not only warning for a long time, but also it's almost accumulating to a level beyond which we should not be able to find even larger risks. And same in the social domain. I mean, we're talking about 9, 10 billion people. Can it really get worse? But what if, in fact, we've just come to the beginning? What if this is truly just the aperitif towards the big challenges? Because I think there's potentially, let's put it this way, the largest ignorance we have is the fact that on the social side, it's not at all about 9 billion people. The numbers are actually secondary to the fact that we're moving from 1.5 billion living with a lifestyle roughly represented by us in this room to a positive development of 4, 5, 6, 7 billion people with the same purchasing power as an average European, and with the same expectations of human well-being as an average European. And that's the big gear, and that big gear is being put in place now. It's happening right as we speak in India, China, Latin America, and even in African nations. Potentially the most positive thing we're seeing in the world today. But of course putting a tremendous pressure on a finite Earth system, which start to show evidence of surprise and feedbacks. And what if it is so that the Earth system so far has provided us with a remarkable proof of resilience, an ability to dampen and slow down and store heat in the deep ocean, keep ice reflecting incoming heat, and storing carbon in the biosphere, and even keeping other agents of change in the system, like methane. And what if it's only now, in 2012, we for the first time get a signal from the Earth system that, dear friends, my ability to buffer is starting to, dwindle. And this could be an agenda we unfortunately need to also address. And how do we communicate that agenda when I feel, and I think we all feel as scientists, that we've come to a point where the last thing a politician wants to hear is problems. And I think that's also one of the issues we need to address. I'll just bring up a couple of more problems though, and then come to sort of say the framework. Now, the question we felt we had to ask 2007, 2008 was, well, we've been doing 30 years of science, we often use this kind of ball and cup analogy to illustrate multiple stable states and thresholds, and we've always put an ecosystem there. The ball is the ecosystem. What if we now have to put the Earth system there and ask the question, are we risking the stability and therefore the ability of the Earth system to provide well-being in the modern world as we know it? And of course, to answer that question, we need to start to define what's a desired state of planet Earth. And I know this has been essentially trying to link these two scientific evidence of the Anthropocene, which is the pressure, and the risk of regime shift, which is the nonlinear dynamics and risks of tipping points. And this has probably been discussed this morning as well. I think, to put it simple, I think there is science now from the fantastic work in glaciology to answer the question, what is our desired state? And that our desired state is what we called to remain in Holocene-like conditions. And one way of putting this evidence on the table is through the ice core data in Greenland over the past 100,000 years. We often show ice core data from millions of years, but it's quite relevant to show a 100,000 year period because we've been modern humans for roughly 160,000 years. So this is a period when we've had the same physical and intellectual ability to develop civilizations as we know it. This is temperature as a good proxy of how it was to live on Earth. And of course, as we know, it was a very variable and jumpy ride indeed for humanity during most of this period. We were hunters and gatherers right through this whole period. We were 2 to 40 million people on Earth. At this point here, you may be aware that Stephen Oppenheimer and colleagues have shown through paleo DNA data that we may have been down to 15,000 fertile adults on Earth. We were stuck in the 3,500 meter high Ethiopian highlands, one of the few places where we still could feed ourselves because most of the fresh water was tied up in the polar regions. It was drought, cold, and difficult on Earth. We come to the point of the Holocene, and we enter what I think rightly should be called today the Eden's Garden, providing the basis for human well-being as we know it. And as you know, we barely enter the Holocene, and we do the most important invention of all in the modern human history. We invent agriculture, and off we go into the sedentary journey of empire building, civilization building, all the way to the point where we're 3 billion people at the point of the Great Acceleration. We're 7 today, committed to 9. Now, however one twist and turn that, the Holocene, despite the fact that the diversity on Earth has been around for millions of years, the genetic base for everything that matters for human well-being. But it's also true, it's only in the past 10,000 years that everything settles in terms of the resources and ecosystems that we know and we've been so clever in using for our well-being. So the fact that we started cultivating food was not because we suddenly invented agriculture, it was because we started to realize, 15th of May, it seems like the temperature is high enough to be able to plant. And I seem to have 100 days to grow a crop and then harvest. Rainy seasons became so predictable that we could talk of an onset window for rainfall, not in months, but in days. Today we can actually have onset in days. And we know we have secured roughly 25 rainfall events to a harvest. And all that settling in of the landscapes and seascapes, I believe is kind of the key to why we started off in this journey. And therefore one can talk of the Holocene as a very important, as a stable state in support of humanity. That's the big challenge then. We're in the Anthropocene, pushing ourselves out of the Holocene stability. This is a period, as you know, with ±1 degree Celsius in terms of temperature variability throughout the period. And the question then is, where are we heading? We used the Holocene reference point as the desired state, and then asking the question, okay, so what's the scientific evidence of what are the environmental processes that are important to be stewards of to regulate Holocene-like conditions? And can we, for those environmental processes, define a boundary beyond which we enter a danger zone, where science indicates the risk of nonlinear changes that could result in feedbacks that could jeopardize the Holocene-like condition? And that was what resulted in the planetary boundary framework, which results in 9 processes being suggested as important processes to regulate Holocene-like conditions. And the interesting part is, of course, that it's not only about climate change, and this whole conference is about the insight that the biosphere, the slow variables under the hood of the Earth system, fresh water, land, biodiversity, and the large cycles of nitrogen and phosphorus, that these 4 slow variables do not necessarily have evidence of planetary scale tipping points, even though Anthony Barnowski indicates that there might be one for biodiversity. But that's not the point. The point is that these show evidence of being regulators of the stability at the planetary scale. That aerosol loading plays a critical role for monsoon stability and also for the feedback systems on soot and other black carbon agents. That new entities of chemical pollution can aggregate to a point where it affects genetic code and therefore the basis for human and animal plant development. And that the stratospheric ozone layer, of course, is also one of the planetary boundaries in terms of protecting and shielding humanity towards undesired influxes of ultraviolet radiation, and that the oceans are critical for the ultimate stability of the Earth system. So this is one way of articulating at least a starting point, a reference point for navigating the more complex world of the Anthropocene. And I really want to emphasize this, that the planetary boundaries thinking did not come out of a vacuum. It didn't kind of come right out of the air. It was really based on 30 years of advancements in Earth system science. It's a twin concept to guardrails, tipping elements, ecological carrying capacity research, many other concepts. It is very much inspired by everything from Kenneth Baldwin's Spaceship Earth to the Herman Daly model of a steady-state economy, and of course building on regime shift and tipping point science coming out of complex systems dynamic and resilience research. And again, it of course asks the question, what are the risks of crossing tipping points from science synthesizing a standard deviation, an uncertainty zone, a kind of a danger zone, and doing a normative choice of placing the boundary at the lower end of the scientific uncertainty. So for climate, we ended up showing that science seems to say that at 350 to 550 ppm CO2 concentration, we seem to risk nonlinear behavior in the Earth system, and we put the boundary at the 350 level. So it's not that the boundary is the tipping point. The boundary is the point when you enter scientific uncertainty. And we also include then processes like biodiversity and land, which do not show evidence, at least, of planetary scale tipping points, but they show clear indications that when you push it far enough, for example on deforestation, you get feedbacks that affect the big systems that do have nonlinear threshold behavior like the climate system. Quantifications were attempted for 7 of these. 2 were not quantified, air pollution and chemical pollution, which is, we can come back to that in a questioning session, but of course because they have such multiple complex agents included. It was done in order to challenge science in particular, but it, to our surprise, I would argue, also resonated very much within civil society, business and policy, which has also triggered a lot of, let's say, dialogue beyond science. But as we speak, the science is the focus, and we're now working on a Planetary Boundary 2.0, to quantify all 9 and update and then kind of self-critically assess the first round. We've entered a discussion and a close project with the World Business Council for Sustainable Development, which you know is a global network with the big companies in the world covering 10% of the world economy, of trying to redefine their business models where they're willing to actually build in a subset of the 5 planetary boundaries that they feel that they can move quickly on in terms of what are 2020 planetary must-haves in terms of a transition towards business models within a safe operating space. And drawing upon science, for example on climate, saying that the IPCC fourth assessment indicates that if we can bend the CO2 emission curve by 2020, we need to follow a 5 to 6% reduction curve to have a 6 to 70% chance of staying under 2 degrees. And if we can do that, that is something that can be scaled down to business level and could be a must-have for Unilever or Walmart or any of the big companies. There's been criticism in the natural science of the planetary boundaries, as you've seen perhaps. The phosphorus boundary was deemed to be too optimistic. Steve Carpenter and Alan Bennett showing that for way before you have the noxic tipping points of the oceans, which was our indicator, you have freshwater tipping points in the basins flowing down to the ocean. So we've rectified that. And we are working very actively now on trying to deepen our, for example, freshwater boundary for the following reason. We concluded that there's evidence to suggest that when you exceed a consumptive freshwater use in rivers of what we call blue water, the liquid water and groundwater in rivers and lakes, of 4,000 cubic kilometers, you start to see nonlinear behavior in river basins. You start to see collapse in terms of aquatic ecosystem services, for example. This was criticized for not being operational at a scale of any relevance for any manager. So we're now working on trying to find twin indicators at the lower level, so basically at the basin scale, building on the research showing how water-driven shifts can lead to tipping points to begin with. And this is work by Lena Gordon and others showing again that land use change, water use change can lead to abrupt shifts in large systems in the world. The work by Schmacktin and colleagues showing that we can today measure quite well when regions get subject to absolute water scarcity in red here, and that we know quite well today for the basins in the world how large portion of water we need to keep in the rivers to avoid tipping points. So roughly, on average, 35 to 40% of base flow needs to remain in rivers to avoid shifting entire landscapes from functioning. We are working right now on doing tipping point analysis of what are the systems that could be driven to abrupt change if we change water use, and based on all this work, try to translate that into a scaled boundary for water, and that's ongoing work right now. Okay, so as I have 5 more minutes, and then I'm through. So this is just then to kind of wrap things up in how does that then, how can we connect this to the policy domain on stewardship? So one is to refer back to the fact that much of the planetary boundary work is inspired by Herman Daly and kind of economic research indicating that we need to think of the economy as a method to supply human well-being, not growth specifically, and that the social domain needs to operate within the life support systems on Earth. This is a simple model, but it is very challenging for development, a kind of a shift in the way we relate between society and the biosphere. The planetary boundary ceiling of biophysical quantitative boundaries for a system process has been also complemented, particularly by civil society organizations. This is Kate Raworth from Oxfam, showing that, well, if that's the case, we certainly have a social floor of human universal rights to ecological space, the remaining ecological space on Earth, which creates a donut model for human development in the Anthropocene. And this is interesting because it addresses the fact that setting quantitative boundaries on the biophysical side just adds the importance of democracy, equity, and a fair solidarity-based sharing of resources among all inhabitants on Earth. We published last week, as a contribution to the Ban Ki-moon Sustainable Development Goals work, a suggestion of how one could merge the social dimensions of development in the world, articulated in the Millennium Development Goals, with a set of science-based planetary must-haves in the Anthropocene from Earth system science to create a set of sustainable development goals which are truly unified. Today, as you know, we have having poverty, hunger, education, health, and then there's a narrative on environmental sustainability somewhere here. Now the point is to say that if we take the model of the economy serving society within the Earth system, and we take a combined approach of social and biophysical goals, it could result in something like this. We suggested with 6 large sustainable development goals, which largely capture what really are the key elements for development, from food security, water, energy, health, institutions, and livelihoods. And to say that within each of these, for example, for energy, we need to set what are the biophysical goals. For example, a 500 gigaton remaining carbon budget for 2-degree target. What are the social goals? Well, universal energy access. And what are the economic policies? Well, take away the $600 billion per year of subsidies to fossil fuel use. Basically having a fully unified set of targets for each of these integrated goals. And we believe that science cannot do this. It's basically taking a set of social goals from equity to health and institutions and linking our Earth system science into these 6. So combining global sustainability with human dimensions across scales. And doing that, we believe from our work, this is a special issue we did in conjunction with the Nobel Symposia work we did on global sustainability in Ambio, showing that however we twist and turn this, however focused we are on bottom-up processes, we need something of the kind of planetary stewardship. We need things to add up at the global scale. And we need to start truly looking at as Unsi Biggs and colleagues did recently, of what are the elements that then can build resilient societies in this more shaky world. On polycentricity from Rockström, for example, and the whole necessity of diversity and redundancy. We can feed the world with this work, shown by John Foley and colleagues, so it's not as if this is a doomsday, dead end. There are transitions that actually can sustainably intensify, for example, agriculture, one of the most important sectors because of biodiversity, energy, water, and climate. There are examples of systems that have gone into crisis and been lifted out of transitioning into a resilient state. And we show in 2 recent books that one can have a fast-track set of policies written here in a book with Anders Wijkman, a former EU parliamentarian, but also that we need big changes in values. We need to have a mind shift also, which we've called a human quest journey. And my final slide is this. So coming back where I started, so basically moving from a paradigm of growth without limits to just the thinking of development within the boundaries of the planet. And being in York, I can of course, and a Swede, I cannot not put this on the table, which is the question of what happens then with a nation state, and then what are the key values that can enable nations to collaborate towards a thriving future in the Anthropocene. And I do believe that the Nordic model, in fact, shows a couple of those elements. And this is not to brag. You may have seen this issue showing that Nordic countries are way ahead in some of the elements that matter for well-being. But the key point here, if you ever read this, is trust. That if there's any parameter where the Nordic countries are outliers, is trust between people who don't know each other. So there's one trust indicator which is between people who know each other very closely. But to have trust between people who don't know each other, and therefore also beyond nations, could be one element in this kind of journey, because it's all about moving from the biophysics to the human dimensions, which I know will be the focus of tomorrow. Thank you very much.